Okay, here we are on challenge 10, and let's look at problem 3. Problem 3 is talking about some volatile compounds. Now the confusing part about this is that X, Y, and Z are not elements like you're used to thinking about. They're compounds. So this might be Q3O, and this might be Q2O, and this might be QO. So what you have to keep track of is that these are compounds, not elements. But the first question, since it's on challenge 10, looks like gases. Okay? So let's start with that. We write down our given. We know that the vapor pressure at 27 degrees, the pressure is equal to, see, now this is number 3A. So the pressure is 750 millimeters of mercury. We know right away we're going to have to convert that to ATM because we're probably going to use the ideal gas law. Okay, 750 divided by 760, 0.987 ATM. Okay, the temperature is 27 degrees Celsius, so we know we have to add 273 to that, so that's going to be 300 Kelvin. And it says that the thing weighed 3.53 grams per liter, so let's just say that we have 1 liter. That way we know exactly how much it weighs. Okay? PV equals nRT. Since we're solving for number of moles, we're going to move everything to the other side, so this becomes N equals PV over RT. Pressure, 0.987. The volume is 1.0 liters. The R, 0.0821. And T is 300 Kelvin. Okay, so the number of moles in this sample at this particular volume is equal to 0.987 times 1 divided by 0.0821 divided by 300 equals 0.04007. Here's what I always do when I'm not sure what to do. I ask myself, what are the units that I'm interested in? They want us to find the molecular weight. Okay, that's really the molar mass. All right? What are the units for molar mass? Grams per mole. Well, here's moles, and here's grams. So if we divide this by this, we'll get the right units. And that's going to be the way clear for this answer. So the answer is 3.53 grams for every 0.04007 moles, and this turns into be... How are you?
Good. How much longer are you going to be?
Good. 5-10 minutes.
Okay.
Is that okay?
Yeah, that's fine.
Okay.
I'll just go next door and do that first.
Okay, thanks, Jeff. Sorry to...
Young's not here, so we're kind of picking up.
Okay. 3.53 divided by 0.0047 equals... Now watch what I do in my calculator. I just put in 3.53. The 0.0477 is already there, so I'm not really gonna, it's not really that, but I just need to flip it over. So I'm gonna use my 1 over x key, and boom, there's my answer, 88 grams per mole. Okay, that's all I have to do. So the answer is 88.1 grams per mole. That's the answer that goes in part A. So look what I did. I made sure that I'm very clear about my answer, 88.1 grams per mole. Now I'm going to go on to B. Determine the mass of element Q containing 1 mole of each of the 3 compounds. Okay, so that's pretty straightforward. We know that the molecular weight of this compound is 88 now. We know that this one's 104, so all I have to do is take that percentage. Okay, so again, I'm going to set it up really clearly so that my grader knows exactly what I'm going to do. So here's X, and that's 0.648 times 88.1, and that turns out to be, notice it's already in my calculator, so I just go 0.648 And boom, there's my answer, 57.1 grams of Q. Okay, for Y, it is 0.73 times 104, 0.73 times 104, 75.92 grams of Q, and then Z, 0.593 times 64. All right, that's, whoops, 0.593 times 64, 37.95 grams of Q. Okay, I'm going to put boxes around those so that the reader knows that those are my answers, and there I am done with B. Now the answer is C. Calculate the most probable value of the atomic weight of element Q. Look at these numbers. This number is exactly half of this number. And I wonder what my relationship is between these two. So 57.1 divided by 37.95. Look at that, that's 1.5. So the relationship here is 1 to 2. The relationship here is 1.5. So this is basically my least common multiple. Now, it could be 37.95 or 38, but it could also be half of 38. For instance, this could be, what's half of 38? 19. So this could be 19, and this could be 4 times that, so that could be, right? So there's 2 atoms of that in here. There's 4 units in here and 3 units in here. So I'm going to go with 19. I wonder if that's going to be the right answer. So I'm going to say, because 19 will go into each, into 37.95 twice, and 75.92 4, and 57.1. Let's just check that. It should be 57.1 divided by 19. Okay, so exactly 3 times. I would say, I think 19.0 grams is the best choice. Okay? Alright, so I'm going to say 19 grams. I put a box around it. Easy to find. Carbon C contains carbon, hydrogen, and element Q when 1 gram is... Okay, remember, this is a combustion analysis problem. So what we're doing here is we are assuming that all of the carbon came from carbon dioxide, all of the hydrogen came from water, and all of the Q is already there. Okay? So here's what we do. We start with our carbon dioxide. 1.37 grams. Okay? 44 grams per mole. So that means, and, let's do one more step. Let's assume that all of the carbon, so that's moles of carbon dioxide, mole of carbon dioxide has 1 mole of carbon, and 1 mole of carbon weighs 12.01 grams. Okay? So then, it becomes 1.37 divided by 44 times 12.01, enter. 0.374 grams of carbon in my sample. H2O. Same concept. I start with 0.281 grams of H2O. I know that the molar mass of water is 18.02 grams per mole. I know that in a mole of water, there's 2 moles of hydrogen, and I know that every 1 mole of hydrogen weighs 1.01 grams. So 1.01 times 2 times my given 0.281 by 18.02 equals 0.0315 grams of hydrogen. And last but not least, I have to add these 2 numbers up, and when I add those numbers up, I get 0.405 grams of those 2 together, and then I also know that the amount of the whole compound, read the given, 1 gram. So I know that the rest of it is 0.595 grams. So Q, 0.5945 grams. Take the molar mass at Q, which I thought was 19, so I divide that, and I get 0.031 grams of Q. I have 0.03 grams of carbon, moles of carbon, sorry. That's moles. Sorry. And I have 0.031 moles of hydrogen. Isn't that interesting? I've got 3, divide through by the smallest one. So the empirical formula is CHQ. Determine the most probable molecular formula. That's interesting. Doesn't really tell us a molar mass of the compound, so I'm going to have to go with CHQ, or perhaps C2H2Q2. But in any case, those are done. Let's box our answers. Let's check one more time and call it good. Okay? Thank you.